Alright, so this is something that I'm doing from a different location, so hopefully the sound quality isn't like horrible, but I guess we'll see. So basically this exercise sort of builds on the last one a little bit, but not directly. So recall from the previous exercise that given such a function f, so what we need to do in the last exercise is f was like, was it homogeneous of order n, and we need to compute its derivative. Here, we'll write it out again. So instead of saying d, so here we're considering f of x times f of t times x, but we're considering it only as a function of t. And so normally in that theorem that we used was a 2-9, I think. So in that theorem, this would be just d1 f of t. But because the function is literally a function of, it's actually a function of both t and x, but we're just treating it as a function of t, I want to specify that we're taking the derivative with respect to t. And so that's why I've written partial t instead of just d1. Okay, but yeah, so what we did in that exercise is, so we used that theorem to compute that this is actually, can be written in this form. We take the ith coordinate of x and we multiply the derivative in the ith direction of f at tx. And let's see here, what we did. Yeah, so what we did in the previous exercises, we actually used this in addition to a few other things to prove something special about functions that are homogeneous of order n. But here we're not doing that. Here all we're using is this fact. So if you want to see the details on how to compute this, it's just an application of one of the theorems from the textbook, so go back to the other exercise and view that. Okay, so they tell us for this exercise, they give us this function h, which is supposed, or h sub x, which is supposed to be helpful. So let h sub x of t equals f of tx, and now let's verify this equation that they gave us. So if we actually want to compute the integral from 0 to 1 of hx prime of t dt, now actually I would prefer to write this as hx prime of tau d tau, so that we're not reusing the variable t, but it's not really that big of a deal. But anyway, so we use a fundamental theorem of calculus, which we haven't learned yet, but are going to use anyways, because I guess that's what we do in this textbook. And we get this. But we know that hx of 1 is f of 1 times x, which is just f of x. Then hx 0 is f of 0. So we subtract f of 0, but we're told that f of 0 is 0, so then this is precisely f of x. Okay, so thus, if we want to compute f of x, which we do, because that's what we're trying to prove, we can write this as the integral from 0 to 1 of hx prime of t dt. Of course, here we're hx prime, we're taking the derivative with respect to t, and so this is integral from 0 to 1, and we're taking the derivative with respect to t, and the function with which we're taking the derivative is h sub x of t, which again is f of tx. And we're taking this, we're integrating with respect to t. Okay, and so now we have this formula for how we can compute this, or we have this alternative formula for partial t of f of tx. So we'll just put that in there. The sum from I equals 1 to n of xi times dif of tx. And this, we're integrating this entire sum with respect to t. And now, because of some theorems, which again we haven't learned because we haven't studied integration, but we're still expected to somehow know how to integrate here, we can pull this sum outside of the integral. And this integral is with respect only to t, so we can actually put the integral in to the right of xi, because xi is just a constant, so we would pull it out. So we have this integral from 0 to 1 of di f of tx dt. And so if we sort of look at the form of this sum, this is actually the exact type of formula that we want, because we've got f of x being equal to a sum from I equals 1 to n of xi times this integral thing. But look, there's an x in here, and so this is some function of x. So therefore, we just set gi x equals the integral from 0 to 1 of di f of tx dt. And then, as we can see above, this works out. So yeah, once you use that, so I think the trickiest part here is actually computing the partial derivative with respect to t of f of tx, but we did that in the last exercise. So doing the last exercise first makes this exercise pretty straightforward. Maybe it's not entirely obvious how to proceed from the hint, but yeah, this is all we have to do. And of course, again, I've mentioned this a lot, the worst part about this exercise is the fact that you have to use facts about integration that we haven't learned yet. But on the plus side, if you just assume those facts, then that can help build your intuition for when you actually study integration. So even though like doing things in this order is technically incorrect because we haven't learned these things yet, at least it sort of starts to help build your intuition. And so once you do actually prove everything for yourself, you can see how you could use these things to go back and sort of reprove everything in order. Of course, the only places where you run into issues is if you're using facts about integrals to prove things about integrals, because that's circular reasoning. But here, these are just sort of differentiation exercises, which can be more interesting when they involve integration. And so I guess it is sort of nice to have them here in the derivative section of the textbook rather than wait until we study integration to be like, okay, so now we're going to go back and do a whole bunch of exercises that are related to differentiation, even though that's not what we're studying anymore. But yeah, however you feel about it, it's just a few facts about integrals that you use for this exercise. Then other than that, it's pretty short once you know how to do it. And so, yeah, that's it.